different. Right? So I'm going to look at not the sort of problems and solutions in action today, but what's going to come sometime in the future. This is, as an academic, that's my job. Right? So I'm not a practitioner. I think about what kinds of problems could be there down the line. So the topic is trustworthy and accountable function as a service. And I'm sure all of you are experts in function as a service, and you probably know about this more than how much I know. And I'm sure you have yourselves been involved in deploying function as a service or using them. So I don't really need to give you an introduction. This is an increasingly popular paradigm. It's different from infrastructure as a service in a couple of respects. Right? So first, we are talking about relatively short-running outsourced computation. So it's not that you fire up a virtual machine and then you let it run for a long time, but rather you have functions that are short and invoked repeatedly. The reason why this is interesting is because there are commercial offerings already. I'm sure you are familiar with that. Google, Amazon, Microsoft, all of them have sort of large-scale commercial offerings of function as a service as a paradigm. The security problems of function as a service are, at the first level of approximation, not any different from any kind of outsourced computing. If you outsource your computing to some remote party, you have to worry about confidentiality of your data, right? So you have to somehow ensure that if you are, if your outsourced computation is going to use sensitive information, you have to have some way of protecting the confidentiality. You also want to ensure integrity of computation. You ask somebody else to do computation for you, you need to be able to trust that they have done the computation correctly and the results are trustworthy. If you don't ensure this, you end up having problems like we have seen many times before. Whenever there is outsourced computation, either the party that's doing outsourced computation is not trustworthy, or they have some security vulnerability. Somebody breaks into their servers, and then either your confidentiality of the data or integrity of results are at stake. Right? So those problems don't go away, even in the case of function as a service. But there are sort of additional requirements. So if you have infrastructure as a service, you need to do resource accounting or measurements at a coarse-grained level. If you're doing function as a service, you are going to outsource small amounts of computation, and you need to do measurements at a much finer granularity than what you are used to. And so all of these problems, the confidentiality, integrity, and then resource measurements, today in infrastructure as a service, and also function as a service, these rely on reputational trust. Right? So if you outsource your computation to Amazon, you don't worry about confidentiality or integrity because you trust Amazon. So you know that even though you are sending your confidential data to a server running on AWS, if you trust that Amazon is reputable enough, they will not abuse your data. They will also take care of installing or implementing enough security mechanisms. You can then rely that confidentiality of the data or results of the computation are reliable. Similarly, for accounting, resource accounting, you entirely rely on Amazon to do it correctly. Right? So you buy a slice, and then at some later point, Amazon tells you that you use this much memory, this much computation time, this much bandwidth, and because of reputational trust, you believe that they have done it correctly and they are not out to cheat you. And then the reason they are not out to cheat you, is that that's their reputation. Right? So if it's known that Amazon has cheated somebody, then their entire business is eventually harmed. So how does this change when you have function as a service? So function as a service, even though today it's provided by the same big organizations who have this kind of deserve the kind of reputation that they have gained so far, in the future this might change, right? So you might be outsourcing computation not just to big services with a level of reputation that you can rely on, but to small-scale providers. Right? So it could be an individual with a powerful personal computer who has some spare computation capacity. Right? So maybe imagine a kid with a fast game PC sitting in his basement, and whenever he's not playing a game, he's willing to make the computation capacity available. And this is not just an idle speculation. There are already startups that are working in this space, where they sort of mediate this kind of spare computation capacity and offer them to people who want to use outsource their computation. So given that this is going to happen, the indications are that there are startups, and why wouldn't anyone use this kind of harnessing this idle computation as a way of a distributed large-scale compute infrastructure? So this is going to happen. So if you assume that it's going to happen, you can go back and sort of ask this question of relying on reputational trust for ensuring confidentiality, integrity, and resource accounting. Is that still a valid assumption? Right? So these small-scale providers, you might not even know who they are. If you're outsourcing it to Amazon, you know it's Amazon, therefore you rely on their reputation. If it's some kid in a basement with a fast computer, you might not even know who they are. They may not have these expertise to protect them, even if they themselves are honest and well-meaning. They may be incompetent, so that if you outsource your computation to some computer in a basement, that might be vulnerable to being hacked or abused in some other way. More importantly, there is also very little to disincentivize them from cheating, right? So you can rely on Amazon to measure how much computation you have used, how much memory bandwidth you have used. But if it's a little teenage kid, the teenage kid might think that they can overcharge you a little bit and earn a little bit more money. Right? So there is no basis for reputational trust, as it is the case with large-scale providers. So this is the setting that we want to work on. So if we take it as a given that a few years down the line, outsourced computation is going to be distributed and not limited to a few very large organizations, how do we ensure confidentiality, integrity, and accounting? So let's start with sort of an abstract model of what we want to do. So we have a service provider who's providing the compute infrastructure. We have a function provider who's designing the functions, and then the function provider provisions these functions to the service provider's computing. So typically this is you as a developer, and this is, today these are big organizations like Amazon and Microsoft, but tomorrow this could be anyone, right? Anyone who has spare computing capacity. Once the functions are provided, clients of the function provider, who could be from the same organization as the function provider, or maybe customers of the function provider, they are going to invoke these functions by sending inputs and getting outputs. And the service provider today measures how much resources were used and provide these measurements and presumably bill for the usage, right? So this is the setting. So you can think about sort of what kinds of security problems arise here. What is the adversary model? What are the threats that we're trying to protect against? So in the case of a service provider, from the point of view of the clients or from the function provider, the service provider can learn the inputs and outputs of function invocation. Right? If you are relying on reputational trust, that might be okay. If you're not relying on reputational trust, you have to worry about how do we stop the service provider from abusing these inputs and outputs. Right? The best way to do that is if you can facilitate function as a service without the service provider actually learning the inputs and outputs. This might seem like a very paradoxical thing, like how can they do outsourced computing if they can't learn the inputs and outputs? But that's what you would ideally want, right? If you don't want somebody to abuse the inputs and outputs, then the best way to do that is to prevent them from knowing this information in the first place, while still letting them do computation that you need them to do. Second thing is that more than just learning inputs and outputs, they might actually compromise the integrity. They might modify the inputs and outputs, or they might run the function that you want incorrectly. So you also don't want that. So if you are a function provider or service provider, you want to ensure that these threats are somehow eliminated. On the other hand, apart from confidentiality and integrity, you also want to make sure that the function provider, the computation provider, doesn't overcharge you as a function provider. So if you outsource some functions, you want to only pay for what your clients used and not be overcharged. So there are different ways in which overcharging happens. The service provider could inflate resource usage, right? So claim that you have used more computation or more memory or more network bandwidth. Or they can claim that there were function invocations when there weren't any, right? So they say that you deployed a function and then 100 clients invoke that, right? Even though there were only 10 clients. So there could be false function invocation. So this is if you don't rely or trust the service provider. On the other hand, the function provider could be malicious. And the function provider's incentive might be to underpay for the resource usage. So use more computation or more memory or more bandwidth, but not pay for what they used. So the solution to this problem should make sure that it's resistant to both a potentially malicious service provider, but also a potentially malicious function provider. And the important thing is that today's setup assumes, of course, you don't rely on the function provider, but we assume that the service provider is completely trusted, and that's how we solve all of these problems. And this is not a keepable assumption going forward. Okay, so now that we sort of have an idea of what the threats we are trying to deal with, we can formulate requirements, right? So we don't yet know how to achieve them, but we can anyway articulate what requirements we want. So first of all, we want security, meaning that the service provider cannot modify the inputs or outputs. The service provider should also perform the outsourced function computation correctly, right? So they should not lie about it, or you should incorrectly execute something other than the function that you outsourced to them. The second requirement is privacy, right? So you want to outsource some computation, but you don't want the server to misuse your data, either the input or output. And the best way to ensure that they don't misuse is to prevent them from learning the input and output in the first place altogether. The third requirement is that you need to be able to account for resource usage, and you need to be able to do that at a fine enough granularity so that even small function invocations can be measured correctly. But more importantly, this measurement should be reliable, so that the client, the function provider knows that the measurement is accurate. They are not, he's not being overcharged. And similarly, the service provider knows that they're accurate, and there's no way for the function provider to underclaim the use of resources. So ideally, these are the requirements that we want. And like I said, at first glance, these might seem like impossible requirements to fill. So typically, when you have a situation like this, for example, when you want to do computation without the party that's doing the computation learning the inputs, essentially there are two ways in which you can do that. One is to use cryptography, right? So you can use sophisticated cryptographic techniques such as encrypted computation, where you send the inputs in encrypted form and have the computation provider operate on encrypted data, send you back the results, so that essentially they are doing the computation that you want without learning the inputs and outputs. So that's one way to do that. And usually this is expensive. Another way to do that is to rely on some kind of hardware protection mechanism. So for that, I have to give you a little bit of background for what are so-called trusted execution environment. So just for so that I get an idea, how many of you have heard this term before, trusted execution environments? Okay, so maybe not that many, so I'll just briefly explain what this is. So by trusted execution environment, I mean any device that has hardware support for three things. The first is isolated execution, meaning that this device runs an operating system and applications and so on. So this is all the red stuff. And usually these are big pieces of software, and therefore they may have vulnerabilities that can be exploited. But in addition to running this standard software, if there is hardware support to run some small pieces of software in parallel to this other software, that's the first property we want. So we want isolated execution, and if there's hardware support for doing this isolated execution, meaning that it's isolated from all the other software. So this other software, if it's vulnerable, it won't be able to interfere or learn what this trusted software is doing. So this is requirement number one. Requirement two is that it's nice to be able to do this isolated computation, but if you want to do something useful, such as, so imagine that this is your mobile phone, and this is like iOS or Android, these are all the various applications you have, and then you want to use trusted software to do something like online banking, right? So if you can run a small banking application, that's great. But then, in order for this to be useful, this small trusted software also needs to have some access to data, persistent data, such as cryptographic keys or state information and so on. So in addition to the isolated execution, you also need some form of protected storage, some way of storing data that's accessible to this trusted software but is not accessible to this other software. Right? So that's called sealed storage typically. Right? So typically the way it happens is there is some small amount of secure storage, such as encryption keys, and then you can use that to protect arbitrarily large amount of data that's needed for the operation of this trusted software. That's property number 2. The property number 3 is if you have such a device that has support for isolated execution, that has support for sealed storage, can you prove this to some remote party? Right? So in the case of online banking, I have a phone that's able to do this, but I need to convince my bank that I'm using such a device. And if my bank is satisfied that I'm using a device with such a trusted execution environment, perhaps they can give me better access to my bank account. Right? Instead of just reading my bank account, they can maybe allow me to do transactions. So this ability to convince a remote party is called remote attestation. And typically the way remote attestation works is that if you have such a device, I'm able to, first of all, verify that you have such a device. I can check what software you're running. And I can also set up a secure communication channel from me all the way into this trusted software. So even though there's a client somewhere else, it can talk to this trusted software even in the presence of this other software. So remote attestation is not just verification, but also establishment of a communication channel. So if all 3 of these properties are available on a device, we say that that has a trusted execution environment. And typically, as opposed to trusted execution environment, these other software is called rich execution environment. Rich because they have rich functionality, and rich functionality comes at the cost of lots of software, meaning that the threat surface is much bigger. Right? So typically, this is smaller and therefore can be better protected. So the reason why this is interesting is that such devices are widely available. They started already in the maybe 30, 40 years ago in the form of crypto cards being used in the banking sector, trusted platform modules that are widely deployed in personal computers. But more recently, in the last 15 or 20 years, every smartphone, every tablet has a technology called ARM Trust Zone. And ARM Trust Zone essentially provides this kind of functionality. And more recently, Intel announced a technology called Intel Software Guard Extensions, which allow x86 processors to have similar kind of functionality. So all of these things, the ability to run some software in a way that's isolated from other software, the ability to have storage that's persistent and protected from other software, but more importantly, the ability for a remote party to verify that this is the case, and then have a secure communication channel from outside running going all the way into this trusted software. So like I said, this is widely deployed, and then we are going to use this kind of availability of trusted execution environment to design a system to protect function as a service, meeting the requirements that we mentioned before, such as confidentiality, integrity, fine-grained resource measurement that all parties can rely on. So if you are interested in trusted execution environment, there are a couple of pointers where you can learn more information about. I think these slides are made available to the audience already. And anyway, if you Google for my name, you will find my webpage, and these slides are already available on my webpage. Okay, so I mentioned SGX, Intel SGX. So a little bit of explanation about what Intel SGX is and how it realizes this trusted execution environment. So typically, Intel SGX has this trusted execution environment not as a sort of separate entity or separate processor, but rather in user space itself. So every process has the normal application code and application data, but it can designate some functions or some part of the computation as a trusted execution environment. In SGX terminology, that's called an enclave, like this. And the enclave has its own code and own data, and the processor makes sure that this is encrypted, and when execution is within this enclave, the enclave data is made available. Right? And the data is decrypted only when it's loaded into the processor, and when it's there's virtual memory and the pages are evicted from the memory, then the processor will make sure that it's encrypted and integrity protected when it goes out, and when it comes back in, it's decrypted and checked for integrity. SGX makes this possible to have both confidentiality and integrity for the data and execution, but also allows remote attestation. So remember that remote attestation is if you are running an enclave on your Intel machine, I as a remote party can ask you to prove to me that you are running this enclave. Right? And then I can set up a channel that terminates in the enclave code itself. So this is what we are going to use to build our function as a service, security application function as a service. And the basic idea would be that every function is now going to be run inside an enclave. And we are going to use remote attestation to verify that the function is running correctly. So this is how we will make sure that the input goes only to the function, and the service provider, whom we don't trust, wouldn't be able to access the input, even though the input will be used for the computation itself. We will also make sure that because it's running inside the enclave, there is a component that is responsible for resource usage measurements, and that's done securely so that the service provider can't influence that. Also, the function provider can't influence that. So there's no inflating the measurements or deflating the measurements, underreporting the measurements, because we rely on the hardware security methods. So at first glance, this is how you do it, but we are probably already wondering or already sort of seeing potential challenges in trying to realize functional service using an approach like this. Right? So the first challenge is that you're going to be running the function within the enclave. You're also going to be running the measurements within the enclave. So of course, the function can interfere with the measurements, right? Because it's essentially in the same process, and even though a trusted execution environment provides isolation between the rest of the process and the enclave, within the enclave, everything is has the same level of access. So that's the first problem. The second problem is that remote attestation is usually it's a complex process. It's okay to do that if you want to measure a large piece of code. But in function as a service, you can outsource small functions. So you need to be able to, if you start doing remote attestation for every function, that can easily get out of hand in terms of the cost of the attestation. The third problem is that when a function provider outsources a function, you can't rely on the service provider to do key management, right? Because you don't trust the service provider. So this might not be so evident right now, so let me come back to that later to explain this. But the intent is that the function provider is going to outsource the function, and the client is going to provide input. These need to be encrypted. We have to do key management for this encryption and decryption. And we can't rely on the service provider to do key management because we don't trust the service provider itself. So we need to find a way to solve this key management problem. The last one, which is the bigger challenge that I'm going to be primarily talking about, is how are we going to do this measurement of time? So I'm not going to talk about measurement of memory usage, measurement of network bandwidth for reasons of time. The slides and the paper that I referred to talk about those. But the real challenging problem is how is this computation time correctly measured? And the reason why this is challenging is because so we have a function here, and the measurement code is going to sort of count how many clock cycles or how many some units of measurement, how many ticks a particular function execution takes, and how to do this in such a way that even though we don't rely on the operator of this machine, we want to be able to measure this correctly. So there are instructions like there is a CPU instruction called read timestamp counter, and I think this measures ticks from the last boot. So we could perhaps rely on that, right? So when we start the function, we read the value of the read timestamp counter, what the read timestamp counter returns. At the end of the function, we can read it again, and then we can see the value that's the number of ticks that I passed is the number of clock cycles that were used. But this is not going to work if there is a virtual machine here, right? Because the virtual machine can, as it virtualizes hardware, it can actually interfere with the values that read timestamp counter returns. Right? Remember that we don't trust the service provider. So we can't rely on CPU instructions like this. SGX itself provides a way to get timestamps. It's called SGX trusted time. So Intel has as part of their firmware, they have a function that allows you to measure time even in the presence of a malicious virtual machine monitor. But it turns out that this can be arbitrarily delayed. So while the function is, while some code is executing on the enclave, the system that's outside can interrupt this execution. Right? So if it's interrupt the execution, SGX get trusted time is not going to be aware of that. So that way, the service provider can inflate the computation time that's required or that's reported by invoking a function, interrupting it, delaying this interrupt handling as long as he wants, and then resuming execution. And SGX, the trusted time, is going to report the entire time, including the interrupted time. Right. So, in fact, there was a paper that sort of tried to address this problem of verifiable resource accounting, and they essentially use this SGX trusted time, like I described before, at the beginning of the function and at the end of the function, and then compute the difference. But the problem is, like I said, the malicious adversary who is controlling the machine where this enclave is running could issue this AEX instruction, which is called asynchronous interrupt, and then impose an arbitrary time delay before he resumes resumes execution, and the time stamps that you get is going to include not just this time, but also this arbitrary delay. Right? So that's the challenge with how to do time measurement correctly. Okay, so we looked at 4 challenges, and in the remaining time, I'm going to show you how these 4 challenges are addressed, and I'll show you some performance measurements. So the first challenge is, what do we do? How do we isolate these resource measurement mechanisms from the actual function code, even though they are going to be running within the same enclave? So out of these 4 challenges, the first 3 challenges are solved in a relatively straightforward way. And I'm going to briefly explain them and then spend the bulk of the time explaining this last challenge. So the first challenge, how do we isolate them? Well, the natural way to do that is to sandbox the function. Right? And this is a kind of natural thing to do because there are sandboxes that are commonly used. In our particular case, we use a sandboxing technology called OWASP, but one could use JavaScript or any other sandbox. So essentially, this is limiting the applicability. It says that we only deal with functions that are written in this sandbox environment. So in this case, it will be a OWASP function, or it could be a JavaScript function, and we'll limit function as a service to that particular setup. But that allows us to provide this isolation so that this function, if this is a JavaScript function, that's not going to be able to interfere with the measurement mechanism that's running in the enclave, but outside this sandbox. So this is straightforward enough. So that's how we address this first challenge, sandboxing. The second challenge is the number of attestation that you would need to do if you were applying attestation in the standard way for every function invocation. Right? So the real problem is key management. How do we do this key management? How do we do this key management and attestation and do it in such a way that it can be done in a scalable way? So the way we do that is to say, so remember that our setup is that there is a service provider, there's a function provider who's going to do the function provisioning, and there's a client who's going to eventually talk to this function, send encrypted input, and get encrypted output back. We introduce a key distribution enclave, which is going to be responsible for the actual key management. So the key distribution enclave, at the time the function provider wants to set up a function as a service, want to provision a function, the key distribution enclave generates 3 key pairs. So my notation is that for each key, plus means the public part, minus means the private part. So there are 3 key pairs that the key distribution enclave will create. The first key is the enclave key. That's a Diffie-Hellman key that's going to be used for establishing secure channel between the client and the enclave later on. The second key, KO, is the output key that's going to be used for certifying the output as having been computed correctly using the function inside the enclave itself. And KR is the resource measurement key. So while the function is computing the output based on the input, the resource measurement mechanism is going to measure the resources used, and that's going to be reported by signing these measurements using this third key pair. And we assume that the client has a similar Diffie-Hellman key pair that's going to be used with the enclave as Diffie-Hellman key pair to set up the channel. Right? So the important thing to note here is that the function provider, when he provisions the function, cannot really know which machine and which particular enclave and which particular SGX instance is going to run that function, right? Because this is the basis of any kind of cloud setup that you might want to do elasticity. You might want to sort of designate the computation to be done by the best available machine at that time, right? So by having this key distribution enclave, we can differ the selection of the actual worker enclave that's going to do the computation, as long as we rely on this key distribution enclave to sort of correctly authenticate the worker enclave and then provision the correct keys. So the way this works is that the function provider first, when he wants to provision a function, he doesn't talk to the worker enclave because we don't know who the worker enclave is yet, but he can attach the key distribution enclave and set up a secure channel. And similarly, when the client wants to invoke a function, again, it doesn't know who the worker enclave is, but it can talk to the key distribution enclave and set up a secure channel. Remember that attestation means not only verifying the machine, not only verifying what software is running, but also setting up a channel that ends inside this trusted execution environment. So once that is set up, the key distribution enclave can then provide these public keys that the client needs to set up a channel to the function and also to get the results back. Similarly, it can send the resource measurement key that the function provider needs to get resource measurements and verify that they were certified correctly. Right? So the resource measurements are going to be signed by the resource measurement key, and the function provider needs the corresponding public key to be able to verify that. And then at some point, at a later point, the key distribution enclave or the system decides which particular hardware is going to actually run this function, and at that point, it's going to authenticate that machine, authenticate the work enclave, and going to give the private parts of these keys to that sandbox, right? To that resource measurement engine. So the function will do the computation, and in order to do that, the client and the work enclave set up a secure channel. They can do that because each knows the other's public key, each knows its own private key. They can set up a DB element channel, and using that channel, it can send the inputs. And when the function computes the result, it can send the results back using the same channel, and the resource measurement mechanism sends the measurement results back to the function provider authenticated using this channel. So again, this is fairly straightforward architecture. The only sort of subtle part here is that by introducing this key distribution enclave, we delay the selection of the work enclave for a later point in time. So essentially, we are doing late binding. Okay, so this is also fairly straightforward. And then the third problem is this encrypting output, which I just talked about. So the bulk of the time I'm going to spend on this last part, right? So how do we measure time? So remember that there are different types of resource usage that needs to be measured. Different functional service systems use different types of measurements, number of invocations, the amount of memory seconds used, the amount of bandwidth used, and so on. So I'm going to just limit myself to the time taken by the computation of a particular function. Right? I'm going to use some notation. So we're going to measure time in terms of ticks. Right? So ticks is some unit of measurement of computation. Each tick might correspond to some number of clock cycles. So this is total computable time, total compute time of function in terms of ticks, and each tick is some number of CPU cycles that can be decided by the service provider. I'm not going to talk about these parts. The slides talk about that in more detail, but I don't have time to go through that, so I'm going to only talk about the time of it. Okay, so what's the problem? I alluded this already in the beginning that we can have a worker that's actually going to execute the function. We can have a separate timer that's going to now measure the ticks that this execution is going to take. The problem is, of course, that this can be interrupted, right? So if it's interrupted, we need to have a way of knowing. So first of all, if there's a timer, the timer needs to know when the worker starts to do the work. So there has to be a way, whenever this external invocation comes in, the timer has to be notified. That's easy enough to do. And there is this risk that while this worker is running, the untrusted service provider infrastructure might interrupt this execution. So if it's interrupted, the timer needs to know when the interruption started, and then when the computation resumed again. So we have to have a reliable way of ensuring that if it's ever interrupted, the timer would account for that and report only the computation time and not the time that's spent outside. So we can't just do that if you only had SGX. Fortunately, Intel has an additional piece of technology that allows us to make this possible. But to explain that, I need to give you some kind of a little bit of a technical background about what happens during these interruptions. Right? So if you think about SGX machines that's running software, so first of all, there are a bunch of CPU registers, including a stack pointer and instruction pointer. And the enclave itself has two data structures that are relevant for us. The first is called a thread control structure. So each thread has a control structure which says whether the thread is now in use or not. So by default, it's free. It's not being in use. And then each thread control structure also has a pointer to what's called a saved state area, which is like a stack. So every time the thread is interrupted, corresponding information is going to be used in this saved state area. And when the thread is resumed, the saved information is going to be written back. So in action, it's going to look something like that. So whenever there's an external eCall is the SGX terminology for starting an enclave. So when there's an eCall, this thread control structure is going to change its state to busy, and execution is going to go through, and the stack pointer and the instruction pointer will change along with the instruction. If there is an interrupt AEX, which is the interrupt signal, if there's an interrupt, then the stack pointer and the instruction pointer are going to be saved on this stack, and the current save state area pointer is going to be updated, and control goes out of the enclave because there was an interrupt from outside. Right? And when the interruption is resumed, again there's an instruction called ERESUME. The enclave gets control back. It reads the saved information so that it can continue from where it left off. So this is how interruptions work in SGX. So we are going to use this as a way to set up our measurement architecture such that interruptions are correctly accounted for. Right? And in order to do that, I told you that we need this other additional piece of Intel technology, which is called TSX, Transaction Synchronization Extensions. TSX was introduced as a way to avoid having locks. Locks are expensive. If you want to have like concurrent computation where you want to ensure the integrity of some data, instead of using locks, you can use this kind of transaction synchronization extension. Essentially what it does is to say, when you enter a piece of code where you want to ensure synchronization, you can define a read set and a write set. The read set consists of the memory addresses that are going to be, that are read by the transaction, and the transaction will abort if at any time during this instruction somebody writes to those areas, because write means that there is a potential conflict. Similarly, a write set is memory addresses that are written by the transaction, and the transaction will abort if anything in the write set is read concurrently. And whenever there is an abort, everything is rolled back. So this is provided by this TSX extension, and we are going to use this in the following way. So first of all, in the SSS stack, we are going to put a magic number. Right? The magic number is something that we choose that is ever unlikely to be the return address pointer that will be written in this first entry of the SSS stack. And as long as this magic number is there, we know that there has been no interruption. Right? So we have a worker, we have a timer that's running all the time, and the timer is just simply waiting for the worker to start. Whenever the worker is invoked using an eCall, we are going to write our magic number here, and we are going to notify the timer that now you can start counting ticks. Right? So that the timer is going to now start measuring how many ticks it's been used. If there is, the code for this is essentially going to look like there is a marker. As long as the marker is what we expect, we are going to sort of go through and count the number of ticks. Right? But we make sure that this is a transaction, so there's a read set and a write set for this transaction. And if there is an interruption at any point, remember what the interruption does. It's going to now write the current stack pointer and the instruction pointer into this SSS stack, which means that it's going to overwrite our magic marker, right? The magic number that we put there. So because it's in the write set, the timer transaction will now abort because a value that we relied on has been written concurrently by somebody else, right? The handling of the interrupt. So the timer now knows that while this magic marker has gone away, it shouldn't count ticks. And the way we would sort of resume this is by having this interruption ERESUME handler. Instead of sort of doing the normal resumption, we now go back and write our magic marker again, right? So that's how we differentiate between this area, by letting this timer know when the interruption happened, because the transaction will abort, and when the resumption happens, because we will have a special interruption handler, resume handler, that's going to put our magic marker again. Right? So I guess having sort of explained that, you can sort of intuitively see how this works, right? So we want to use transaction synchronization as a way for the timer to know when the interruption happened and when the resumption happened. So I'm not going to sort of explain the details of how we do measurements and how we measure memory consumption and network bandwidth and so on. So I just want to give you some numbers of what kind of overhead that's involved. So we measure two kinds of overhead. One is the actual starting of the measurement process itself, and we sort of separate between a cold start where we have to start everything, and a warm start where we assume that the container is already running and the enclave has already been created, and we only want to measure the actual key agreement between the client and without any computation, right? So we just want to measure the sort of latency for invoking a function. And the sort of takeaway here is that these are fairly small numbers. So the baseline, without using our instrumentation, would take something in the order of 3.1 seconds, and with the instrumentation it's slightly more. So that's for the actual machinery itself. The actual computation, of course, we need to use some kind of benchmark suite. So we used a standard benchmark suite, and again, the important thing is to know that so there is an overhead, because we are counting ticks, and then the machinery to count ticks. But it is a reasonable number in the sense that it's single digit in terms of percentage points. So you probably already sort of realized that this is on top of running a separate thread. So there's already, you are executing the function, and there's a timer thread that's running all the time. Right? So in effect, you pay double the cost because you're running a timer, and this is on top of the timer. So we'll come back to this and how reasonable it is that you double the cost because you want to do accounting and input confidentiality and output integrity properly. Okay, so I hope I'm convinced that we can do this using SGX, and the overhead is limited. Now let's look at these the potential drawbacks. So whenever I present this, the first criticism I get is this double the cost that we talked about, right? So if you want to do measurements, you have an extra thread running all the time, so that imagine that you had like one machine running at full capacity. Now you would be able to only run this at half capacity because the other half is used for measurement. So at first glance, this looks like a bad thing. On the other hand, it may not be a bad thing because if you have heard about SGX, many of you said you didn't know, but if you have sort of followed SGX, there's been also a number of the so-called microarchitectural side channel attacks against SGX and against processes in general, because modern processors use all kinds of optimization, including things like speculation, pipelining, and so on. And so you may have heard names like Spectre, right? This is an example of microarchitectural side channel attack. It turns out that one of the defense mechanisms against such microarchitectural side channel attack is to use a second hyperthread where you can implement this protection mechanism. So if you're already going to be doing this second thread that's needed for side channel defenses, then we will be able to use that thread to mark time as well. Right? So in that sense, it may not be a bad thing. There are a couple of other things. So remember that the way we measure time is by counting ticks, and then whenever there's an interruption, our transaction fails, and we'll not count until the transaction resumed again. So there is a round-off error involved. So it can result in a little bit of overcharging or a little bit of undercharging depending on how you do the round-off. So again, I don't want to go into details, but if you're interested, we can talk about that later, or you can look at the paper. But the round-off is something that you can control as a service provider. And so this is what I mean in the end, that each provider can decide what value they are going to use for a tick, and that's also going to depend the type of architecture, the computing architecture they use, because the number of clock cycles that corresponds to a tick depends on the architecture. So this is not something that you can sort of deploy, design once and deploy, but you have to customize that for each application. I'm not going to talk about this as such, but let me, since I'm going to be out of time and I want to have time for questions, let me go to the end. So the messages that I want to leave you with are, function as a service is popular, but we can envisage a time where function as a service is going to be outsourced not only to reputed providers, but to a large number of different types of organizations, including individuals with extra computing capacity. And if you have a setup like that, then you need strong security. You can't rely on reputational trust alone. And for function as a service, you also need to be able to do resource consumption measurements at a fine enough granularity. And I showed, based on our work, how this can be done using SGX, which is a trusted execution environment for Intel processes. And this work was part of a paper that was presented at Cloud Computing Workshop at CCS. CCS is like a top academic security conference. You can find the paper itself by going to my research page. SEM papers are behind the paywall, but if you go through the author's page, then you are taken directly to the paper. The code is also available. I don't have a link to the code here, but if you look at the paper, there's a link to the code as well. So if you take the paper from here, you'll be able to find the GitHub code. There are a number of possible future work, but in the interest of time, I'm going to stop here and perhaps answer some questions that you might have. That's all I have to say for now.
มีใครมีคำถามไหมครับ
So how do you envision this mechanism be deployed? Meaning that are you hoping that Intel would implement this as part of a mechanism for people to measure time, or is it going to be deployed by all these startups that are doing this?
Right. It's going to be developed. So we implemented it by using an off-the-shelf SGX machine, right? So the example startups that I mentioned before, Golem and so on, they could do that today, right? They have what they need to do is instrument their sort of function as service infrastructure to be able to have our timer thread and the key distribution enclave and so on, and allow the remote part, the function provider and the clients to be able to attest these enclaves and then outsource computation. But they could do it today. So we wouldn't need anything from Intel, essentially.
มีคำถามอื่นไหมครับถ้ามีคำถามอื่นก็เดี๋ยวขออนุญาตโฆษณาให้ทางอาจารย์โซกันนะครับอาจารย์โซกันนี่เขากำลังหานะครับนักเรียนนะครับที่จะไปเรียนนะครับมีทุนให้นะครับทั้งป.โทป.เอกนะครับถ้าใครสนใจก็ติดต่ออาจารย์ได้นะครับ
I don't know if you told them that I will be here during the break, so if someone want to ask questions in front of an audience, they can always come talk to me.
แล้วเดี๋ยวช่วงเบรกอาจารย์โซกันก็ยังอยู่นะครับว่าใครมีคำถามก็สามารถมาคุยกับอาจารย์ได้นะครับก็ถ้ามีคำถามแล้วผมขออนุญาตนะครับขอเสียงปรบมือให้อาจารย์โซกันก็ต่อไปเดี๋ยวเราอยากเบรกนะครับก็ทานเบรกในห้องนี้ได้